One of the things that we do in the electricity and magnetism part of physics is to look at the electric field due to different charge distributions. And one of those charge distributions that come up is a spherically, uniformly distributed spherical shell of charge. So I want to calculate the electric field due to this charge using a Monte Carlo calculation. Now I'm going to go over some of this groundwork, and then we're going to build this in Python. I just want you to know this is actually the third time I've recorded this. Both times were interrupted. So I wrote some stuff, and I'm not going to rewrite it. I want to get to it and do it, Okay, so suppose I have a metal sphere, and I add extra charge to that. If there's no other external fields to move things around, that charge will be evenly distributed the excess charge will be evenly distributed on the surface of the sphere. And two important things happen from that's usually said in the book. But I'm going to show you how it works. And number one thing is, if you look at the electric field inside the sphere, it's zero, the zero vector. And the electric field outside the sphere would be just like this is a single point charge located at the center. You can kind of conceptually understand how the first part would work. If I'm right there at the center of the sphere and I want to find the net electric field, I can find the electric field due to, let's say, these two opposite charges, and they're pointing in opposite directions. The electric field is, so they'd cancel. And then so for every point, I can find another opposite point on the opposite side of the sphere, and the total electric field would be zero in the center. Now, if I move off to the side, it's not so obvious, but it's still true. And then outside, it's not so obvious that it's a point charge unless you get really far away. Then this does look very, very small, and it looks like a point charge. But this should work even if I'm right outside the sphere. Okay, so let's review how we find the electric field due to a point charge. Suppose I have a charge Q at some vector location RQ, not at the origin. And I have some location down here that I want to find the electric field. I'm going to call this the location RO for observation location. Then the vector from the charge to the location would be this, right? It's just a displacement. So it goes, I'm going from here to there, so it'd be RO minus RQ would be this vector R. With that, I can use the following definition for the electric field due to a point charge. The electric field E is 1 over 4 pi epsilon naught Q over R squared, where that's at the magnitude of R squared. You can't take the square of a vector, so you find the magnitude of that vector. And then you have to multiply by this unit vector R hat. And if you don't do that, you just get a scalar value. And that's not good. Because what if I have 2 point charges? What if I have another point charge down here? Then I want to find the electric field due to it also, and it's going to have a different electric field, and then the total electric field will be the superposition of these two, so I add them together. If I just have a scalar value, then I can't add these. They have to be added as vectors. So I need this R hat, which is a unit vector in the direction of R, and that turns this whole calculation into an electric field equation, a vector equation. So that's how I'd find the electric field due to 2 charges. If I have 3 charges, I would just do this again and again and again. I just find all the electric fields, and then I add them all up, and that's my total. And that's what I'm going to do. And so let's say I want to do 1,000 points. So now what about the Monte Carlo part of this calculation? So Monte Carlo really means using random numbers. And how do you make 1,000 spherically distributed points, uniformly distributed points on a sphere? I mean, you could do this, right? The problem is that I could easily spread them out this way in a circle. I can say, okay, break it into 2 pi radians divided by 1,000, and then each one gets a little shift around. It's not so hard. But what about in spherical distribution? I have different ranges, right? I have a theta and a phi, and one goes from 0 to pi, and one goes from 0 to 2 pi. So you can still do it, but it could be a little tricky. So in the Monte Carlo calculation, I'm not gonna uniformly distribute them. I'm gonna randomly distribute them with a uniform random distribution, so they'll be mostly uniform, but not perfectly, and that's okay. But to do that, I need to use the random function in GlowScript v Python. So GlowScript v Python is Python with some important modules in there. If you did this with some other method, if you used NumPy, you might use a different, or you could import random. But this is the random functions already in there, and this returns a number between 0 and 1. So let's go back over to this, because I want to build a sphere. I picked a sphere of radius 0.1 meters, total charge of 1 times 10 to the negative ninth, and there's my Coulomb constant, 9 times 10 to the ninth, 1 over 4 pi epsilon naught. Oh, it must have not. Look at that. I also need to know the thickness of this, right? I need to pick. I can't have it infinitely thin. So I'm going to pick 0.001 meters. So what I'm going to do is actually first generate these random points in the shape of a sphere, and then go and calculate the electric field wherever I want, and using the same method right here for each of these points. Okay, so let's jump over to Python. Actually, I'm going to first make a cube of points, radius from negative point R to point R, and then we'll make it into a shell. Okay, so let's jump over to Python. I already got started because I told you I got interrupted before. So here is Python. Here we go. So this is GlowScript v Python. I'm going to give you the code for this, so don't worry about that. Let's see, make it a little bit bigger. So I have R, I have RT, I have Q, I have K. Let's just do this. Let's just do n equals 1. Oops. N equals, whoops. N equals 100. So one of the ways to make 100 points is to have that my maximum thing is 100. I'm going to start with lowercase n is 0, and then I'm going to say while n is less than n, do the following: print n, and then increase n. And this isn't the best way to do it. Okay, there are a lot of ways to make more points, but this is the way that I think a lot of people it makes sense to them, and I think that's important for the code to make sense, and so that it can be your own. So this is run this and see what happens. And there you go. See, it goes up to 99. The first one was 0, so that is 100 points. If it's one extra point, I don't really care anyway. Okay, so now let's just print 100 random numbers. Let's do this differently. Let's do this. So let's just say print random, just so you can see what that looks like. And so they're all between 0 and 1. But I actually want to go from negative R to R, right? Because that's how big my sphere is going to be. So let's do this. How can I get a number between R and negative R and R? So I can do this, R times, parentheses, 2 times random minus 1. So random, 2 times random is going to be a number between 0 and 2. And then I subtract 1, and it could be as low as 0 minus 1, which would be negative 1. It could be as high as 2 minus 1, which is 1. So this gives me a number between negative 1 and 1, and then I multiply by R, and I get between negative 0.1 and 1, and 0.1. Let's just check. Something bad happened. I missed a parentheses. That's what happened, I think. Print. See, yep. There you go. So all these are between negative 0.1 and 1, and they should be uniformly distributed. Okay, so there we have those. Now what I want to do is actually make a sphere. So a sphere, a point is going to have a 3 coordinates, x, y, and z. So let's make a sphere. I'm just going to make a sphere with these 3 coordinates. So I'm going to say this. Let's just do this a simple way. We'll make it better. So I'm going to say sphere. I'm not going to give it a name because I don't really care. The position, the sphere is a 3D object in GlowScript. It has a position, which is going to be vector, this, for the x coordinate. Oops. That. So I'm going to say copy that, comma, that, comma, that. So it has 3 random numbers. And then it has a size, a radius. Let's just give it a radius of RT. And let's just run that. And we don't need to print it, because who cares? Let's just run. And there you go. There's 100 random points in a cube. And it's kind of hard to see that it's a cube 1 because my picture's in the way. Let's move this down here. So let's just increase this up to 1,000, because if I did it for 100, I can do it for 1,000. How's that? See, that looks like a cube. Let's just do 5,000. Okay, now it's really starting to look, so it does look uniformly distributed, and that's good. That's a good check, right? And it is kind of cool, and we can kind of zoom in through it just for fun. I don't know. That's cool. Okay, and you can make them different colors. You can make it, you can do all this sort of stuff. So let's change it back to 1,000. Okay, but I don't want a cube. What I want to do is generate all these numbers, these points, and only keep them if they are between r plus RT over 2 and r minus RT over 2. Does that make sense? So because that's not the thickness of my shell. So let's say this. Let's generate a random number. So I'm going to go over here and copy this. I'm going to actually cut it. I'm going to call it RT. And I'm going to say RT equals that. So this will still do the same thing. It just had a random number, and then I plot it. But I don't want to plot it. I don't want to make the sphere unless, so I'm going to say this. If the magnitude of that, of RT, is greater than or equal to r minus RT over 2, right? Because then I'm going to say that the radius of my sphere minus a little bit, and mag RT, is less than or equal to r plus RT over 2. So there's my thin little region. Only if it's between there should I make a sphere. Okay, so I'm going to tab indent. That's in my if statement. And I'm only going to increase in if I make a sphere. So I'm still going to make 1,000 points, but they should be in a shell. Let's see if it works. Isn't that nice? It looks like the Death Star. So there's my 1,000 points in a sphere, and we can zoom in through this too, just for fun. Okay, and it's kind of hard to see that it's hollow, but it is hollow. I'm kind of impressed. Let's make that 5,000. Let's just see what happens if I make that 5,000. Yeah, you like that? Look at that. Okay, let's put it back at 1,000. We can change it to 5,000 later. So I have all these points, but I actually need them as charges. So let's do this. Let's say charges equals this. This is an empty list. And what I'm going to do is add that sphere to my list of charges. So I'm going to go down here, and I'm going to say charges. Oops, I got to spell it right. Charges equals charges plus, and then put a square bracket around this. And that will add that sphere to my list, and then I can go back and look at things in the list. I can go through the list and stuff like that. In fact, I'm going to add one more thing. I'm going to say here, Q equals Q divided by N. So this will give it an extra property for each one of those charges of Q, which they're all the same. I didn't have to do that, but I just like to do that anyway. So now if I run it, nothing looks different. But I could go down here and I could like do something like this. Print charges 33.pos. This will print the position of charge, the 34th charge, because the first one's 0, whatever that may be, and it's some random number. And there it is. Okay, so that makes sense. Okay, so now I have my charges. Let's go ahead and calculate the electric field right in the center of that thing. So I'm going to say RO equals vector 0, 0, 0. And now what I want to do is to go through each one of those points and, 1, calculate the vector R from the point charge to RO, and then 2, calculate the electric field due to that charge, and then 3, add it to the total electric field. So I need to start with the total electric field, E net equals the vector 0, 0, 0, and then every time I calculate a new electric field, I can add it to that. So let's do this. So, and having charges as a list allows me to do something awesome like this. Let's change this to just 10. And then I'm going to say for charge in charges. So charge is the variable, charges is the list, and I'm going to go print charge.pos. So it's going to go through each element in that list, call it charge, and while I'm calling it charge, I'm going to print out the position. And so there's just 10 of them, and I can print the position all 10. See? So I can use charge as one of those list elements. It's really nice. So now let's turn that back to 1,000 because 10 is just not nearly enough. So the first thing I'm going to do is calculate the temp R vector. I'm going to call that, could I call it R? I haven't used R yet, have I? Okay, let's say R equals RO minus charge.pos. So charge.pos is the vector location of each one of those individual charges, and R0 is not a thing. It's RO. That was a typo. So that's that. And then I'm going to calculate the electric field due to just that one piece, and I'll call it DE because it's a differential electric field. And it's going to be K times charge.Q times the unit vector R, which is in closed-curve V Python, it's built-in function for that. It's called norm R. And then I need to divide by the magnitude. Again, there's a built-in function, magnitude R squared. In Python, squared is star, star, not hat. Now I'm going to add that piece to my total electric field. I'm going to say E net equals E net plus DE. And that's it. Let's just go ahead and then print E net equals E net, comma, let's put the units newtons per coulomb. Let's run it. Okay, and so it's at the center of the sphere. It should be close to 0, and you're thinking that's not anywhere near close to 0. But I think that it is because, and let's run it again, see if we get something different. I mean, we're talking about a 1 nanocoulomb charge. It should have very high electric fields at this close. So it can fluctuate quite a bit, but it's not like 100 or anything like that. So I think that does give me the correct K, Q, R, yeah. Okay. Now let's move outside the sphere and let's just check, and then we'll make a graph. Okay. So let's say I move RO to, it's a sphere of radius 0.1, so I'm going to say 0.3. That's all I have to do is change that one vector location, right? I can do that. And I get that from my electric field. Now, let's just calculate the theoretical value, assuming that it's a spherically distributed thing, which isn't quite. E theory, I'm just going to calculate the magnitude, is K times the total charge Q divided by the distance from the center to that observation location, which is going to be 0.3 squared. So KQ over R squared. And let's print that out. E theory equals E theory. And it's a spot check, right? Okay, so it's theoretically it should be 100 newtons per coulomb. I got 98.7. That's pretty close. And then the X and Z components of that are very small. So that's pretty good with just 1,000 data points. I could increase that to 2,000, and it should get a little bit better. But every time I run it, it'll give me a slightly different thing. Okay, so that looks like it's working. But what I want to do is actually plot the magnitude of electric field as a function of distance from the center. It should be 0 as long as I'm inside the shell, and then drop down, then be 1 over R squared, just like the theoretical stuff. So let's just see. Now to do that, I'm actually going to make a function to calculate the electric field, so I don't have to just do it a whole bunch of times. So let's make this. Let's comment out this, and let's make a function def enet, and I'm just going to give it RO. So in Python, we can make a function. I'll include a link down below to my tutorial on functions. I don't need this anymore. So there's my start of my function, and in that function, I'm going to give it an R0, and I want to calculate the electric field. So I need that E temporary. I'm not going to call it E net. E temp equals, I'll just call it ET, equals vector. It's the same thing. Vector 0, 0, 0, and then this has to be indented. 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 This is ET. ET. But everything else is okay. There's my RO, R, okay. And then I need to say return ET. So down here, ENet is now a function. So if I put in vector 0, 0, 0, it should work. Okay, that other one wasn't a function. And there you see I get something very close to 0. If I put in 0.3, just like I did before. So it's giving me the same thing. It's just I have it as a function now. Okay, so now that I have it as a function, I can actually move my observation location and make a graph, and that's what I'm going to do now. So let's make a graph. And I apologize for not putting lots of comments in here. I'll try to add the comments in there later when you have the link to the code, so you can play with it to your heart's delight. So I don't need to print that. Well, I'll leave it there anyway. So the thing I'm going to do is make a function. So I'm going to say g1 equals graph, x title equals r in meters. I'll include a link down below to graphing. And then y title is going to be equal to, should I plot the magnitude or just the x component? Let's do the magnitude. It's going to be E, let's just do this, E in newtons per coulomb. And then I need a graph to plot. So I'm going to say F1 equals G curve, color equals color dot blue. I can actually do theoretical versus, yeah, let's do that. So let's put a label, Monte Carlo. Let's make another graph, F2, G curve, color equals color dot red, label, oh, I didn't put label, label equals theory. Okay. So now I need to start with my value of R. So I need another name for that. RS for step equals vector 0, 0, 0. And then I'm going to say dr. What's my step size? So let's say that's 0. Let's say it's a vector. Vector 0.00100. Now, while rs.x is less than 0.3, I'm going to move all the way up to 0.3 where I was before. Then I'm going to do the following. Step 1 is to calculate. I'm just going to plot the electron. I don't even need to calculate it. I'm just going to plot it. So did I say magnitude? Yeah. So I'm going to plot f1.plot the x component, which is rs.x, and then the y component is going to be the magnitude of enet rs. And so that's really kind of weird that you can do that, but you can. I can actually put a function, two functions really, because function number 1 is the one I defined, and function number 2 is the magnitude. I can put that right there in the plot, and it'll just do it. Now what I want to do is increase my value of r. rs equals rs plus dr. So that's going to move it up, and then it'll eventually get up to that value, and we should have a plot. Let's just see if that works. And it didn't. A plot must be an rs.x mag enet rs. The magnitude of it. The plot must be an ordinary number. Let's just do this. Mag enet rs. Print that. And then run that and see what happens. Okay, it did print that. rs.x is the x component of that. f1.plot mag. Let's just do this. rs.x. Let's see if that works. Okay, that did work. Oh, you know what happened? I suspect that I got two. Let's do this. Mag enet rs. And I'm not going to go, I'm going to go to 0.9 times r. Because I think if I get at the border, I could be right on a charge and I could get an infinite electric field. No? An ordinary number. Quantity plot must be an ordinary number. Maybe I'll do this. E temp equals, oops, not that. E temp is just, let's say, E net of rs. That's fine. And then I'm going to plot the magnitude mag E temp. It's got it like that, right? There we go. Okay. Pretty happy. It's not 0. Let's fix this a little bit more. Let's put width equals 400, height equals 300. Just makes it a little bit easier to see. Okay. And this is going up to, yeah, so it's at the border, which is kind of weird that it gets that high. But let's just continue. Okay. So now that's up to the thing. Now I can just keep going up. Not sure why that won't let me do that. Okay. I don't need all this stuff. Okay, now I'm going to say while, let's say rs, I think it's going to work, but let's say rs is equal to vector r plus 0.0100. So I kind of like skipped over the edge. Now I can do the same thing. So now while rs.x is less than 0.3, I'm just going to do the same thing. Let's see. Delete, 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 tab. Okay, let's run that. It should work. Okay. Yeah, that looks right. But now what I want to do is actually plot the theoretical for if I'm outside the charge. I'm pretty happy with this. So over here, I'm going to actually calculate E theory equals K times Q divided by the mag rs squared. I'm only calculating the magnitude, so I can do that. And then I'm going to plot that. F2 dot plot rs dot x E theory. Did I spell that right? Check. Look at that. That's good. That's just good. Come on. Now let's change this to 3,000. Let's just see what happens. And you'll notice what I really do like is that this doesn't just jump straight up to here because it should be close to 0, which it is. But once you start getting really close to that edge, the randomness of those points really takes over. They don't absolutely cancel. But there you go. I mean, I think I've solved this problem, right? Outside the sphere, the electric field is just like a point charge. Inside, it's mostly 0, and you can see it is close to 0. Theoretically, this should be straight along like there and just jump straight up. But there you go. Okay, so I'm going to try to remember to include those things down below. What did I say? Functions, maybe a tutorial on lists, something else I said, graphing. Okay, but I hope you enjoy that. I really had fun, and I'm so glad it worked. And on top of that, that is just awesome. I love that. Okay, later.